Hello and welcome to this lecture for our plasma physics course. This is lecture 26. As you'll remember, if you've watched lecture 25, we've been talking about the MHD equations, looking at isotropic, ideal, various combinations. Today, we're going to have a short discussion of some topics that are going to be important in many fields of plasma physics. In particular, we're going to talk about MHD equilibrium. I'm going to assume that you all know what equilibrium means. Equilibrium means force balance, essentially. And we are going to look at somewhat specific cases. And in particular, we are only going to be talking about static equilibrium and isotropic equilibrium. Those are at the same time. The static means that the plasma velocity, which we've been indicating with U, is going to be equal to 0. In general, that's not necessary. And in many physical systems, from tokamaks to magnetosphere, Jupiter's magnetosphere, you name it, there is rotation, there is some flow of the plasma, but adding that physics into the system makes it, of course, more complicated, and we're going to only discuss the easiest circumstances. But before we even do that, there is something that is again important in many fields, in particular in experimental fields that could be nuclear fusion, but not only. And that is what is called the virial theorem. I don't know why it's called the virial theorem, but that's what it's called. This was proven in the 60s. There isn't much that we're doing that wasn't proven in the 60s. And to my understanding, the proof comes from the Russian physicist Shafranov, but it's something you're going to find into any textbook. Okay, here's what we're going to do. We're going to start by assuming equilibrium, and we're going to show that you cannot have MHD equilibrium unless there is some external element, factor, actor acting on the plasma. Or to state this differently, and let me try to fix the spelling there. we're going to show, that's what the virial theorem shows, that the plasma cannot confine itself. That would be very convenient. There's some configuration where we start up the plasma and then the plasma is just going to stay there because it's keeping itself confined, and we can get fusion power out of it. That would be wonderful, but that would also violate some physics that we're going to discuss now. So that is not possible. Okay, we're going to assume again that the equilibrium is static. The virial theorem is going to work even if the equilibrium is non-static, but we're not going to get into that. And I'm going to use a tensor form that is in our textbook, but we actually have not discussed in detail. But it's pretty much a rearrangement of terms in our equilibrium equations. Or actually, I could say that this is the conservation form. If you have or you will deal with fluid dynamics, you'll see that often it is convenient and it is used and natural to write equilibrium equations or equations in general in conservation forms, which means that there is some quantity and there is some divergence of some other quantity. I'm not going to define what the conservation form means, but this is what it is for our problem. Okay, T is what is called the stress tensor. Let me put that in writing for you. And it's defined as follows. It's going to be P perp, P perp, P parallel, and 0 everywhere else. If we assume that the magnetic field is in the Z direction, and that's for convenience, but it's just a matter of setting our coordinate system in a way that makes the problem a little more treatable. P perp is actually the isotropic pressure plus B squared over 2 mu naught, and P parallel is the isotropic pressure, wrong sign, minus, not plus, B squared over 2 mu naught. Again, that's just a way to rearrange the terms. And you can also write the stress tensor as P perp times the identity tensor minus B plus P parallel times BB. If you substitute this expression, you'll see that you get the exact same thing. And B hat is the unit vector parallel to B. Okay, that's all we need. And again, I'm setting my system of coordinates so that the magnetic field is in the Z direction. And let me stress this again. I'm looking at system that is isotropic, but since there is a magnetic field in my system that introduces preferential direction in the system, a degree of anisotropy, and that leads me to define a p parallel and p perp in my system. Okay, so what do we do? Let's take the dot product between the coordinate vector r and the tensor t. That's going to give me a vector, and I'm going to take the divergence of it. Why on earth would I do that? Because that's going to help me prove my theorem. And this is a vector identity. This divergence is actually going to be equal to r dot divergence of t. I'm just distributing the product, and then there's going to be t dot divergence of r, which is an entity vector. So that's going to give me it's going to give me the trace of t, that is the sum of the elements on the diagonal of t. And let's see what we can do here. Let's see how this goes. Could have gone worse. It's actually put it where I didn't want it, but it got the right word. All right, trace of t. Again, this is a tensor identity. So I've not done anything yet. Okay. Now, what I'm going to do next is let me call this equation 1. And I'm going to integrate it over an arbitrary volume. Let me call it V, which is delimited by a surface S. S is just the boundary of V. And let me step back. Let me call this one and this 2 so that I can use equation 1 in equation 2. What that does is tell me that the divergence of t, I'm looking at equilibrium, the divergence of t is 0 because it's an equilibrium. And what I have is now the integral, I'm going to do this maybe a little quickly, but it shouldn't be too hard. B squared over 2 mu naught over the volume, that's going to be equal to the integral of, I'm going to turn this into a surface integral, P plus B squared over 2 mu naught, and dot R minus B squared over 2 mu naught, that's the other piece. In case that's not obvious, I switched left and right, left hand side and right hand side of my equations. Okay, here I have R dot B times N dot B. And since I put the vectors in there, ds is not a vector. And let me be explicit. ds is equal to n hat ds. So n hat is the outward pointing normal vector to s. Almost there. We're going to do a proof by I'm going to assume that the virial theorem is false. That is, my plasma is confined, it's confined by itself. Then I'm going to pick S to be outside the plasma. What that, a consequence of that assumption is that on that surface, this is going to be a lowercase p, grazie, thanks, sorry. P is 0, this is outside the plasma. So there is no plasma there. And in fact, there is no external currents. I can extend, S can be anything. I can send S to infinity. Without changing the value of my integral, because I'm never going to encounter an external current or anything that's confining my plasma. I'm working under the assumption that there isn't anything else in the universe other than my plasma confining itself. Well, but if I do that, and the plasma is confining itself, then B must go down as I move away from the plasma, at least as fast as a dipole. Or in other words, B of S must be some constant over R cubed, or less than that. Just because there is nothing else that can generate. It's just a matter of geometry. If R goes to infinity. We're getting there. Then my integrand, you look at here, P is 0, I only have B squared. B squared R ds scales like 1/cube. And I'm integrating this over a surface. That means that I'm most multiplying times R squared as R goes to infinity. That is my right-hand side goes to 0 as R goes to infinity. But now let's look back at the left-hand side. Here I'm just integrating pressure, which is positive, B squared over 2 mu naught, which is positive, over a volume. The volume could be anything outside the plasma, that integral is 0. In the plasma, that integral is finite and positive. And that's clearly a contradiction. So that leads me to conclude it was false to assume that the plasma could confine itself. Therefore, the virial theorem is proven. We cannot have a plasma confining itself. And that's the bad news for today. Well, it's kind of old news, but if you didn't know, now unfortunately you do. Okay, let's move now briefly to MHD equilibrium, starting from what are the equations. And let me remind you that we're just going to look at static and isotropic. MHD. Square that. Well, all we're going to have is grad P equal to J cross B, because velocity is 0. And then we have divergence of B equals 0, that always works. We're looking at equilibrium. That is, I'm setting time derivatives to 0. That means that the curl of B is equal to mu naught J. And that is pretty much it. In general, I should have another equation that tells me something about the divergence of J, but you can see that this equation already implies divergence of J equals 0. The reason being that the divergence of a curl is automatically 0. Also, Ohm's law is pretty much useless. Because Ohm's law, let me write it. Actually, in general, even for resistive MHD, I will have eta j, but I'm setting this to 0. I'm setting this to 0. Well, all I've got is that the electric field is 0. Now, what we have is the first equation is the force balance equation. This one is going to give me a relation between pressure and magnetic field. And that equation says that the pressure forces must balance the Lorentz force. And we're going to look at a couple of ways you can do that, but another thing or two to look at is well, the force balance equation really only involves J perp, and that is the component of the current that's perpendicular to the magnetic field, and that you can easily get from a vector identity, and that's B cross grad P over B squared. And this is what is called the diamagnetic current. Now, oops, sorry, had an accident here. Let me make sure that the parallel component of the current I can get from, sorry about that, from divergence of J equals 0. The reason why I spent a couple of minutes to emphasize this part is that this is one way stellarator equilibrium calculated, and this is actually not as straightforward as you may think. It's actually rather controversial, and I'm not going to get into it, into the details, but if you, let's say, work on CTH and you want to look at what different people are doing with the equilibrium calculations for stellarators, you'll see that not everybody's going to agree on the right way to do this, on what is the right way to do this. In fact, what you could write is using divergence of B equal 0. See that J is equal to J perp plus J parallel B hat. And this is going to give me dot b dot grad j parallel over b plus divergence of j perp is equal to 0. And again, that may not make everybody happy. Okay, we have already talked about beta and how we can look at the magnetic effect of magnetic field as an effect of pressure, as an effective pressure. It is magnetic pressure. We just used it in the proof of the virial theorem. And what we are going to do next is to look at some specific cases so that you can get a feel or an idea for how the stuff works. And we're going to start from what is called the cylindrical pinch, which is sort of the easiest way you can make an MHD equilibrium. And note that this is going to be a one-dimensional configuration. What that means is that there is only one variable that appears in one independent variable that appears in our equations. That's going to be the radius. We're going to assume system of cylindrical coordinates. I'm going to look at something that looks like this, where here we have z, little r, and theta. And b is going to be equal to b theta of r, while j, you can easily get it from the is in the theta direction. J is going to be in the z direction. You can just take the curl and see what happens. And that is what is called an azimuthal, which is spelled nothing like what I wrote. Azimuthal. Field. Okay. Just put in, I'm going to skip steps, but I'm just going to put in the information I just mentioned in my force balance equation, and notice that my azimuthal field satisfies the divergence of B equals 0 requirement, because divergence of B is going to be 1 over R, the derivative. Well, let me just write it. It's the derivative with respect to theta of B theta. The other components are 0, so I'm not even going to write the equations. But theta does not, B theta does not depend on theta. It's only a function of R, and therefore that derivative is 0, and the divergence of B is 0, as it should be. Now, let me plug my assumptions in my force balance equation. You do that, again, I'm going to skip some steps. You'll find I can use a total derivative or a partial derivative, matter of taste at this point, because we have already assumed that nothing depends on anything other than R. But this is all I'm going to get. That the derivative with respect to R of P plus B theta over 2 mu naught is going to be equal to B theta squared over mu naught R, where this comes from the coordinates of my system. The fact that I'm working in cylindrical coordinates. Okay. If that's the term on the right hand side is essentially the B log B term. Okay, so yeah, no, it's coming from the curvature of the magnetic field. Okay. That's the J cross B term. Sorry about that. Okay. What I was trying to do was, yes, I can integrate this to give me the pressure as a function of R is going to be P0 minus B theta square, again, function of R, over 2 mu naught minus, take the mu naught outside in this integral, the integral between 0 and R, B theta square over R in the R. Notice that B theta needs to go to 0 for R equals 0 to to make this reasonable. That is, B theta is generated by the current that flows in the Z direction, unless there is a singular current flowing on the axis, which we're excluding. B theta needs to go to 0. You can get it from Biot-Savart's law. The current encircled by circled where of radius R goes to 0, the magnetic field on that circle also goes to 0. Okay, so that's one more definition. What P0 is the pressure on axis. So in general, you could have various types of equilibrium. Depending on the current that you have. This is called a pinch because it is the current that we drive into the plasma that creates the magnetic field, the dB theta field. Does not violate the virial theorem, in case you wonder. And a couple more things for completeness. This is called a Z-pinch in plasma physics. And it's one example of an approximation of three-dimensional system. As I said, there can be many different options for making this equilibrium. There is something I'm not going to get into, but you may come across. That's called the Bennett. Let me check my spelling here. Bennett with two T's. They're basically analytical profiles that will give you an equilibrium of this type. So explicit expressions for B theta, J, Z, and P. Another option is what is called the theta pinch. I'm just going to go over it quickly. We've got two more I would like to discuss. The theta pinch is also a one-dimensional configuration, meaning that there is only one coordinate that matters, and similarly to the Z pinch or zeta pinch, the only coordinate that matters is the radius. The difference is the direction of the field. Now, the magnetic field, not the current, is in the Z direction, and the current instead is in the azimuthal direction, where both BZ and J theta are only functions of R. Once again, divergence of B is trivially satisfied. That is just the derivative of BZ, which again only depends on R with respect to Z, and that's of course 0. And J theta is going to be -1 over mu naught d BZ dr. Just taking the curl. From this expression, I'm going to go quickly, but write a couple more steps because they're faster. We can see that the momentum equations reduces to J theta BZ equal to dPdr. Got J cross B on the left-hand side and graph P on the right-hand side. The radial component of the momentum equation is the only one that's not automatically zero. And the pressure is also only a function of R that follows from the momentum equation. You cannot have derivative of the pressure in any other direction because there is nothing to balance it. So the only way to have force balance is for the pressure to only depend on the radius. Putting pieces together, I get that the derivative with respect to R of P plus BZ squared over 2 mu naught is equal to 0, which I can easily solve as P plus BZ squared over 2 mu naught equal to a constant, which I can call B0 over 2 mu naught. Where B0 is going to be the field where the pressure goes to 0. So I can interpret it as the external magnetic field. Yeah, almost fits. Okay, so again, I should highlight something that I didn't for the Z-pinch. That is, okay, these are our equilibrium equations. This is our formal solution. What do I actually do if I want to calculate an equilibrium? Well, you need to assign either, in this case, BZ or P as a function of R, and that in a theoretical calculation you can do arbitrarily. You can put in anything you want, and that's okay. In practice, if you were to build one of these, which people did at the beginning of fusion research, you can take measurements from your experiment or use some other physics to figure out what the correct shape of these functions is going to be. And once you've assigned one, you calculate the other one. And for practical purposes in here, you can calculate. You can assign either pressure or the Z component of the magnetic field. Okay. So actually, people did build theta pinches at the beginning of research, and they kind of work okay, but they have big losses at the end. If this is a cylinder, there is no confinement in the Z direction. The plasma just goes out, worse than a mirror because there isn't even the mirror. And that clearly doesn't make it type of configuration that is going to have much of a future. I'm going to discuss only one more configuration, which is what is called the general screw pinch. This starts looking a little bit more like modern day fusion experiment. In practice, you could take CTH and imagine you cut it somewhere, you straighten it, you unscrew the helix, and this is what you get, a general screw pinch. Or do the same thing with the tokamak, except you don't have to unscrew the helix, you just have to cut it and straighten it. In fact, what is called the straight tokamak approximation, which is obtained by neglecting the effect of toroidal curvature on the plasma, is described by the equations of the general screw pinch. Now, this is still a one-dimensional configuration. But B is going to be equal to B theta of R plus BZ of R. So this should look pretty much like a combination of the previous two configurations. In a more experimentally relevant configuration, B theta corresponds, let's say, for a tokamak, corresponds to the poloidal field, and BZ corresponds to the toroidal field. I'm just trying to get my thing to write what I want. Okay, now we've sort of done all the preparatory work, so we know how to do this. Divergence of B equals 0 gives me 1 over R dB theta, which is a function of R d theta, plus dBz, also function of R dz equals 0. And this is trivially satisfied. Now, when I take the curl of B, I'm going to find, well, a combination of what I found before. That is, Jz is, well, let me start from J theta. Be a little more orderly. J theta is going to be minus 1 over mu naught dBz dr, and Jz is 1 over mu naught r ddr of rb theta. Then when I do the momentum equation or force balance, J theta Bz minus from J cross B, that's what I get, Jz B theta in the R direction is going to be equal to dPdr. Not surprisingly, each one of the first two terms is something we've already worked with. So not surprisingly, all we get is the sum of the two configurations we looked at before, which makes it extremely convenient. What we obtain is that the radial derivative of P plus B theta square plus Bz square over 2 mu naught plus B theta square over mu naught R is equal to 0. And that's the force balance equation for the general screw pinch. In principle, the force balance equation is non-linear, meaning that we have the J cross B term that appears as curl of B cross B, and that's a non-linear term in B. However, just because of the way we pick the geometry and how the vector algebra works out, the theta pinch and Z pinch equations or forces just add linearly. It's just a straight sum. Okay, now this is really simple, but it's already got sorry about that. It's already got a lot of information that can be taken from here. We are not going to have the time to really go into detail, but let me point out a thing or two. First, I mentioned when we were talking about the theta pinch that you need to assign one of P or BZ. Here it is again. In this case, we need to assign two between P, B theta, and BZ. So there are two free functions. For instance, we could assign B theta and BZ, and then we calculate the pressure. Or we could assign BZ and P, and then calculate B theta, which is what you will do in a tokamak. Working with the Grad-Shafranov equation, which is the tokamak equivalent of what we've written here. We could do various things. One useful quantity is that we've already discussed is the safety factor, and I'm not going to do this in detail. Well, maybe Well, let me clarify how this is done, or will make no sense. I can use this creature, my equation here, the general screw pinch, as an approximation of a toroidal device with a major radius R0. Then sorry, I can calculate the rotational transform and the safety factor. Let me just do the rotational transform part. Well, okay. Iota is going to be equal to delta theta. That's the angular rotation along of a field line in the poloidal plane, in the theta direction. That's my poloidal plane, for one toroidal revolution. Well, here I don't have a toroidal revolution, but I can make an equivalent of a toroidal revolution by saying if this is the approximation or the mock-up system for a torus of radius R0, I can call this to be the integral between 0 and delta theta in the theta of my field line, and this I can transform into an integral between 0 and 2 pi R0 in dz of d theta dz, where d theta dz is the direction of, well, it's calculated along the field line. Then what you do is use the field line equations dr dz is equal to br over bz of r. Well, this is 0 because br is 0, and d theta dz is just b theta of r over r bz over r. Sorry. And notice that I need that r in the denominator to make dimensions match. Okay. Work out the algebra. Iota of r is equal to 2 pi r0 b theta over rbc. And q of r, safety factor, is equal to 2 pi over iota of r, and that's RBZ over R naught B theta. And that is the expression that you occasionally find also for tokamaks, and that's the cylindrical approximation of the safety factor. Okay, we're going to close it here, and maybe there is going to be one more lecture, maybe not. I'm still deciding. If so, if there is one, I'll see you then. If not, thank you for making it through the whole course.